Hello everyone, I'm Wei Liu, a PhD student from Software Performance Analysis and Reliability Lab, Concordia University, Canada, under supervision of Peter Chen. In this paper, we propose an approach to locate the origin of SQL queries in database-backed web applications. From online shopping to social media, many database-backed applications dare to interact with the underlying database, such as MySQL, to store and access data. At the same time, the database will record the problematic SQL queries, such as NoSQL queries in logs. The testers and developers may want to know where these SQL queries are generated in source code. This is important because it's the first step towards understanding and debugging the issues. So it comes up with the problem we're going to solve in this paper. Where is the origin of the SQL queries in the source code? However, locating the SQL queries in the source code could be challenging. When using the ORM framework, developers do not need to manually construct the SQL query. Instead, they call the ORM API and it will generate the corresponding SQL query automatically and dynamically. In this example, developers call the entity manage.find to query the owner, and the ORM framework generates a SQL query to query the database tables owner and path. This ORM generated SQL query does not explicitly exist in the source code, so it's not possible to locate where the SQL queries are generated in the source code by doing string match. Besides, the dynamically generated highlights make locating SQL queries more difficult. On the other side, ORM configuration options may affect how the SQL query is generated, which makes locating challenging. In this example, there are two entity classes, pet and owner, in the source code, set by the annotation entity. They map to the database tables pets and owners separately, set by the annotation table. One owner may own multiple pets. When developers configure the fetch strategy as equal, the ORM framework will retrieve all the associated pets at the same time. To do so, the ORM will generate a sequence to query the database tables owners and pets using join. If replacing the strategy with lazy, the ORM framework will retrieve the pets when needed. In this case, the ORM generated sequence queries the database table owners only. To address these changes, we propose an approach SLocator to locate the origin of the given SQL queries. It contains two parts, statically inferring database access and locating the paths that generate a given SQL query. First, it statically analyzes the source code to generate the control flow graphs and traverses them to generate control flow paths. For each ORM core in the path, it infers the database access, uses template SQL queries to get the control flow paths with database access. Then, given the SQL queries, it preprocessed them. Finally, for the preprocessed SQL queries, it applies information retrieval technology to match the most possible control flow paths. In the first part, the approach statically infers control flow paths with database access. Given the source code, it statically analyzes the source code to generate the control flow graphs. Specifically, the control flow graph is a directed graph, where the nodes represent the basic blocks and the edges connecting the nodes represent the transfer of control. The entry point of the control flow graph is a web request handling method. Then you traverse the graphs and generate three control flow paths, path 1, path 2, and path 3. The control flow path is a sequence of methods called in the control flow graph. For each ORM API core in the path, it refers to the database access using template SQL queries. Take the path 1 as an example. The core of persist owner is translated to a SQL query inset into owners, values. In the second part, the approach locates the past for a given SQL query. Given SQL query, it first pre-processes it. It removes the generated variables, column names, and dynamic values. Then it computes the score for every control flow path. These control flow paths are generated in the previous part. It applies information retrieval technology to compute the score. We will illustrate it in detail on next slides. Finally, it outputs the ranked control flow path for the given SQL query. The path with a higher similarity score will be ranked higher in the result, and is more likely to be the path that generates the SQL query. For example, the path 3 has the highest score within the given SQL query, hence it ranks at the first. The approach combines the syntactic similarity and the semantic similarity to compute the score. For the syntactic similarity, it computes the cosine of the vector of Q and P, the vector of name and the weight vectors based on the time frequency and inverse document frequency. For the semantic similarity, it computes the jacket of the features of the Q and P. The features of name are the set of accessed tables and operations on tables. Taking the SQL query and the control flow path as an example. The vectors are weights on the terms, and the features are database tables, owners, and pets, while the operation is snapped. The approach supports different types of SQL queries as an input. When using SQL session logs, all the SQL queries are input to SLocator. When using individual SQL queries, single query in the session logs is input to SLocator. The approach also supports different granularity to locate the SQL queries. For request granularity, the approach locates the web request handling methods that generate the given SQL query. For path granularity, the approach locates the control flow path that generates a given SQL query. We also use different metrics to measure our approach. For static aggregation, the top K represents the percentage of SQL queries that are successfully located in the top K results. The higher the volume of top K, the more effective the approach. We evaluated our approach on 7 study applications. We also compare SLocator with a baseline approach, which applies text search to locate the origin of a given SQL query. When using SQL session logs as the input to the approach, the origin of 45% of SQL queries can be located in top 5, and almost 89% can be located in top 5. When using individual query logs as the input to the approach, the origin of more than 48 of the SQL queries can be located in top 1, and almost 75% can be located in top 5. In the previous RQ, we evaluated the overall localization accuracy of the SLocator. However, the SQL queries may have different complexities such as lengths, which may affect how the SQL query performs. In this RQ, we evaluate the accuracy of SLocator in the localization path for SQL queries with different lengths. The SQL queries are classified into 3 buckets based on their length, namely bottom length, middle length, and top length. We evaluate an approach on these 3 buckets of SQL queries separately. We found that SLocator achieves better localization results for short SQL queries compared to long SQL queries. For the SQL queries with length in the top 1 set, SQL queries present good localization results. The top 5 request is 73.2%, and the top 5 for parse is 17.5%. In this RQ, we use small SQL queries to illustrate how SLocator helps localize database access issues in database-backed web applications. In this case, the SQL query sets the database by stream matching, which could be relatively slow. For this slow SQL query, SLocator returns the control flow path that generates it. By examining the control flow path, we found that The web request handling method retrieves and displays all owners on one page. A solution is to add pagination so that only a limited number of owners will be retrieved and displayed for one page. In conclusion, we first discussed that locating the SQL call rows in the source code is a challenge. To address these challenges, we propose an approach that uses static analysis and information retrieval to locate the SQL call rows. Then, we evaluate the approach on overall SQL call rows and SQL call rows with difference. And last, we illustrate how SLocator helps locate slow SQL call rows. Thank you. That's all of our presentation.